Bismillahirrahmanirrahim. It's me Sabah Sayed and I'm here with the topic of physical quantities. It's the second lecture of chapter number 1 of class 9 physics of Punjab textbook board, which is also used by FBISE. Here, what are physical quantities? All measurable. The word is measurable. All measurable quantities are called physical quantities such as length, mass, time and temperature. These are called physical quantities because they could be measured. And physical quantities possesses at least two characteristics. One is numerical magnitude and other one is unit in which it is measured. For example, if the length of a student is 104 cm, then 104 is its numerical magnitude and centimeter is the unit of measurement. Similarly, when a grocer says that each bag contains 5 kg sugar, he is describing its numerical magnitude as well as the unit of measurement. It would be meaningless to state 5 or kg only. Here in first picture you can see the length of a student is 104 cm. If we could say that the length of a student is 104, then what does it mean? It is meaningless. Or if we say that the length of a student is centimeter, then it would also be meaningless because both of unit and magnitude combine to form a physical quantity. Similarly, also for the case of sugar, when we call it is only 5, so it is meaningless, or kg, it is also meaningless. When we use both 5 and kg is equal to 5 kg sugar, then it would be meaningful. So physical quantities are divided into base quantities and derived quantities. Here we have base quantities. There are 7 physical base quantities which form the foundation of other physical quantities. These physical quantities are called the base quantities. Base quantities are quantities on the basis of which other quantities are expressed. Base quantities are as follows. There are 7. Number 1 is length, number 2 is mass, number 3 is time, number 4 is electric current, number 5 is temperature, number 6 is intensity of light, and number 7 is the amount of substance. All these are base quantities on the basis of which other quantities are expressed or derived. Now base units. Base units, the unit that describe base quantities are called base units. Each base quantity has its SI unit. In first row you can see we have quantity and units. In second row number and symbols are present. In third row you can see length is a base quantity and its units is meter, which is represented by small m. Mass is another base quantity and its unit is kilogram. Time is third base quantity and its unit is second, which is represented by small s. Electric current has unit of ampere. Intensity of light has unit of candela. Temperature is represented by capital T and its unit is Kelvin, which is represented by capital K. Amount of substance has unit of mole. These all are base quantities and base units. The units which used to express the quantities are base units. Here we have derived quantities. Derived quantities are those physical quantities which are expressed in terms of base quantities are called derived quantities. These include area, volume, speed, force, work, energy, power, electric charge, electric potential, etc. These quantities that are expressed in terms of base quantities are called derived quantities. Basically, derived quantities are limitless. They have no limit. As you know, base quantities are only 7 in numbers. Similarly, in this aspect, derived quantities have no number. They are limitless. Similarly, derived units. The units used to measure derived quantities are called derived units. Derived units are defined in terms of base units. They are obtained by multiplying or dividing one or more base units with each other. The unit of area and the unit of volume. Similarly, the unit of area is meter square and for volume is meter cube, are based on the unit of length, which is meter. Here in this table you can see the quantity and its unit. First of all, we have speed, which is represented by small v, and its unit is meter per second. Meter is also base unit, and second is also base unit. By dividing second by meter, we get a new quantity, which is speed, and which is derived quantity. Similarly, for acceleration, when we divide second squares by a meter, when we get acceleration, which is a derived quantity. When we multiply 3 meters with each other, then we get another quantity, which is volume, and whose unit is cubic meter or meter cube. Force is also a derived quantity. Pressure, density, charge, all these are derived quantities. In this animation you could also see derived units. Now we have prefixes. Prefixes are the words or letters added before SI units such as kilo, mega, giga and milli, etc. Some of the quantities are either very large. For example, here we have 250,000 meter, or some are very small. For example, 0.002 watt or 0.000002 gram, etc. SI units have the advantage that their multiples and submultiples can be expressed in terms of prefixes. For example, divide 20,000 by 1000 to express it in kilograms, since kilo represent 10 raised to power 3 or 1000. So here you can see how to present in terms of prefixes. First of all, we have 20,000 gram. When we divide 20,000 by 1000, then it will be equal to kilogram. So it is equal to 20 kilogram, or 20,000 gram could also be written as 20 multiplied 10 raised to power 3, which is equal to kilo. Here is the table for prefixes. In first column you can see prefixes, and in second column you can see the symbol of prefixes, and in third column you can see the multiplier of the prefixes. Hexa is represented by E and its multiplier is 10 raised to power 18. Peta is capital P and its multiplier is 10 raised to power 15. Tera is capital T, Giga is capital G and its multiplier is 10 raised to power 9. Mega is capital M, Kilo is small k, Hecto is H small h, Deca is DA and its multiplier is 10 raised to power 1. Deci is small d and its multiplier is 10 raised to power minus 1. Centi is C, Milli is M, Micro is micro, it is a Greek letter whose name is mu, and its multiplier is 10 raised to power minus 6. Nano is N, Pico is small p, Femto is small f, and Auto is small a, and whose multiplier is 10 raised to power minus 18. Here is the property of prefixes, which is double prefixes are not used, like kilo microgram or microfemtogram could not be used. These are all wrong. For example, no prefixes is used with kilogram because it also has a prefix which is kilo. So here you can see in first example 200,000 meter second. When we convert adding 3 zeros into 10 raised to power 3, then it will be 210 raised to power 3 meter second. As we know, 10 raised to power 3 is equal to kilo, so it will be equal to 200 kilometer second. In next example, we have 480000 watt. When 3 zeros will be equal to 10 raised to power 3, then it will be equal to 4800 kilowatt. Or when other 3 zeros will equal to 10 raised to power 6, then it would be equal to 4.8 megawatt. And in other example, 3 and it has 3, 6 and 8 zeros, and it could be written as 3.3 into 10 raised to power 9, which would be equal to 3.3 gigahertz. These are the examples for positive prefixes, and now the green color shows the examples for negative prefixes. meanings. Here you can see 0.00002 gram would be equal to when point is shifted three digits right from its position, then it would be equal to 0.02 10 raised to power minus 3 gram, and when it is shifted 6 points from its digit, then it will be equal to 20 into 10 raised to power minus 6 gram, which is equal to 20 microgram. And similarly, in other example, we have 3 3 6 7 8 digits, 8 zeros before 8. So when point is shifted 9 digits right on the right side, then it would be equal to 8.1 into 10 raised to power minus 9 meter, or 8.1 nanometer. Similarly, here is the mass for various objects, which could be very large or very small. Here 10 raised to power 24, 22. These are the mass of Earth. Similarly for ocean, elephant, and all these. Now next is scientific notation. A simple but scientific way to write large or small numbers is to express them in some power of 10. In scientific notation, a number is expressed as some power of 10 multiplied by a number between 1 and 10. The moon is 384,000,000 meters away from Earth. Distance of the moon from Earth can also be expressed as 3.84 into 10 raised to power 8 meter. This is form of expressing a number is called the standard form or scientific notation. Here in this digit you can see we have 8 digits after 3. So we shifted our point on left side 8 digits. So 3, it is equal to 3.84 into 10 raised to power 8. This is the way of expressing scientific notation. This saves writing down or interpreting larger number of zeros. For example, another number 62750 could be expressed as 62.75 into 10 raised to power 3, or 62.75 into 10 raised to power 4, or 0.6275 into 10 raised to power 5. All these are correct. For how much digits we shifted our point, it's up to us, but the number that has one non-zero 4 digit before the decimal 6.275 10 raised to power 4 is preferably be taken as standard form. Similarly, standard form of 0.00045 is 4.5 10 raised to power minus 4 second. The standard form for a scientific notation is one digit before the point. It's called the standard form, or considered as the standard form. So next is measuring instrument. Measuring instruments are used to measure various physical quantities such as length, mass, time, volume, etc. All base quantities or derived quantities are used to measure by measuring instruments. These instruments are used in past were not so reliable and accurate as we use today. For example, sundial, water clock, and other time measuring devices used around 1380 were quite rude. On the other hand, digital clocks and watches used nowadays are highly reliable and accurate. Here we shall describe some measuring instruments used in physics laboratory. Here you can see sundial or other water clock which are used in past, but nowadays digital clocks are used which are more accurate and reliable. Here is the meter rule, which is first measuring instrument. A meter rule is a length measuring instrument. It is commonly used in laboratories to measure length of an object or distance between 2 points. It is 1 meter long, which is equal to 100 centimeters. Each centimeter is divided into 10 small divisions called millimeters. Thus 1 millimeter is the smallest reading can be taken using a meter rule and is called the least count. Here in this picture you can see 1 centimeter is equal to 10 millimeter. 1 centimeter is divided into 10 small patches or lines, which is equal to 1 millimeter. The The small line in a meter rule or a scale you can see is millimeter. So millimeter is the least count of meter rule. Here is the precaution for measuring length. While measuring length or distance, eye must kept vertically above the reading point. The reading becomes doubtful if the eye is positioned either left or right of the reading point. Here in figure A, you can see the eye is not right above the reading point, so it is wrong way to observe the reading. So when it in point B or figure B, you can see the eye is right above the reading point. So it is the correct way of reading or checking out the reading of any measuring length. The measuring tape is the second measuring instrument. A measuring tape consists of a thin and long strip of cotton, metal or plastic, generally 10 meter, 20 meter, 50 meter or 100 meter long. Measuring tapes are marked in centimeters as well as in inches. This is used to measure length in meters and centimeters. A measuring tape used by blacksmith and carpenters. Here these are measuring tapes which you have seen in your houses, etc. In measuring tape, it is also equal to used to measure length, and it is used by blacksmith and carpenters, etc. It also has least count of 1 millimeter, similarly as meter rule. That's all for today's lecture. Hope so you have liked my videos. Thanks a lot. Thanks for watching.